This week we start the unit 10 of the course, which is a unit on universal compression. Till now, we have been looking at design of source code and design of compression procedures, where where you see a sequence of symbols. Let's call the sequence X from some X n. So this is this alphabet, and you see n symbols from that alphabet. And what we do is we assume that actually this sequence corresponds to realization of a random variable x1 to xn, and we assume that those random variables have actually taken the value x1 to xn, and we assume further that this x1 to xn actually are generated from a fixed distribution. This xi are distributed according to p, and what we have been saying is x1 to xn are independent and identically distributed with common distribution p. But of course, there may or may not be any p. You just have this data. This is just a sequence of symbols, and this modeling that we have been doing and we have been using here is we can think of it as I called it in the earlier lectures. We can think of it as probabilistic modeling. Probabilistic modeling. Probabilistic modeling, and yeah, which we use to come up with some theory for universal compression. But but it's not that the symbols were actually generated from this distribution. In particular, we have also been assuming that we know this distribution so far. Perhaps this probabilistic modeling is fine because this is one theory and we are giving some performance guarantees for our algorithms. But perhaps you can, perhaps one objection you can raise to all this is who gives you this distribution P, and what happens if we don't know the distribution P. And that's what we will do now in this unit. We will look at the compression problem where there is no P given to you. You are just given this data. And we'll focus on this probabilistic modeling itself. So we will assume that this data was generated from an IID distribution, but the distribution P is not known. Okay. So such algorithms, compression algorithms, which do not assume the knowledge of P are called universal compression algorithms. And they assume the generating distribution is unknown. Okay. All right. So that's what we will look at now. While the generating distribution is unknown, for this course, we still assume that this distribution was an independent distribution. Each symbol was generated independently. However, the theory that we'll build can extend to a larger class of models. It can go beyond just IID distribution. It can include Markov random variable, Markov chain, Markov processes for generating these random variables. And there are partial results available even beyond that when you have, say, hidden Markov processes. Yeah. So to make this problem more tractable, we need to start by setting a benchmark for us, a benchmark for performance. And the earlier benchmark for performance that we have been working with was sort of an absolute benchmark. We were looking for codes which were optimal, which sort of attain the minimum average length for a prefix-free code. The benchmark that we'll pursue in this part uh, is slightly relaxed. We so we need to specify this benchmark of performance. Okay, and this relaxed benchmark is called the redundancy. So what is this redundancy? So instead of asking for the best possible code, what we will ask for is a code that competes with the best possible codes. Okay, that has performance comparable with the best possible code, and we want to minimize this deterioration in performance. Okay, this formulation is inspired by formulations in learning theory where similar ideas are followed. Okay, in fact, it's a set of same people who formulated this problem and who were working in learning theory. So let's give that formulation. So you are given a code C, be a prefix free code. So let's restrict to prefix free codes. Zoom out a little bit. So you're given a prefix free code C. Okay. Note that a prefix free code and its description need not, we are restricting to error free codes. And the description of the code and how it operates doesn't depend on the distribution. It's just a mapping from alphabet the to the binary sequences. So you can describe this code without knowing the distribution. Okay, and you can always compute the average length under this for this code for a distribution P, although it's not known to you, but there is an average length. So you look at all sequences x of length n. You look at the probability of that sequence. That's since it's an ideal distribution, that P n of x, and let Lx be the length that you assign to the sequence, that your code assign to the sequence. Be a prefix free code that assigns a code word of length Lx to the sequence x. Okay, so this is the average length of this code. From this, we will compete with something that knows more than this code, something that actually knows the actual distribution. So imagine there is a fictitious code, and that code knows the actual distribution. Or maybe there's a fictitious algorithm which knows the actual distribution. What is the performance of this algorithm? In fact, what is the best performance of such an algorithm? We saw that such an algorithm can never do better than n of n times HP. Right? So yeah, we are off by 1 bit. Okay, let me write it this way. It cannot do better than, the average length cannot be better than h of Pn. You may be off by 1 bit. We are ignoring that 1 bit here, but you cannot do better than this. So what we are interested in is this difference, which we call the redundancy of this code for n length sequences. So Rn is code for sequences, and then the model that we are evaluating under Pn. This is a given distribution, ideal distribution P. This is what I'm defining as the redundancy of C for Pn. Okay. So this is the performance which our given code, that's the performance we go with. This is the performance our code will have for a model P, which is not known to it. Just a side remark here, this is an IID distribution. This h of Pn therefore is equal to n times HP. Okay. Of course, the code doesn't know the distribution. Okay. So what is the worst case? So it doesn't know the distribution. So we have this clause for different Pn. What we are interested in is the worst case redundancy of a code. So worst case over all distributions. So this we denote by Rn of C, and this is defined as max over all P in this family of distribution over X. So this basically this calligraphic Px is my notation for all distributions on X. Remember that all these distributions live in the so-called probability simplex. right? So that typically I'm just drawing a triangle, but it's a higher dimensional object where it's a set of all PMFs basically. So this is my notation for this thing, Px set of PMFs on X. So take max over all such PMFs of Rn of C comma Pn. Okay, this is the worst case redundancy, and our goal is to look for code C. So this is the performance for this is the measure of performance. Worst case redundancy of a code. This is our measure of performance for the prefix free code C. And we want it to be as small as possible. Note that we are competing with a benchmark which is n times HP. So this grows linearly with n. And therefore, what we want to happen with this guy is we want it to be smaller than n. It should be of the orders. It should be much smaller than n. Something like square root n to the power 3 by 4. All that is fine because at least order wise the redundancy, the error will be smaller than n. Okay. If you tell me that there is a code which has redundancy n, then it may not be such a happy answer because already the performance, the benchmark for performance is n times HP, and if you have redundancy of n, well, it's not clear if you're doing any good. Okay, so this is the worst case redundancy of a code. The ultimate benchmark that any code should aspire to is what we'll call the min-max redundancy. That's the best that a code can do. Min-max redundancy of a code. This is the minimum. I'll denote it by Rn star, and so I'm not displaying the dependence on the alphabet size, but this depends on the alphabet size. Okay, the size of this set X, the cardinality of the set X, but I'm not displaying it in the notation. This Rn star is again defined as max. So you want the best code. So min over all C of Rnc. So if you unroll everything, this looks like min over all C, the best code, the worst case distribution on X of the average length. So we assume that this guy gets generated by P, IID distribution from P, and the code word has length Lx minus NHP. So it's a min-max redundancy measure. Okay, what is the we are looking for the best code which minimizes the worst case error. Okay, that's what min-max redundancy is. And the question we want to address is how large this Rn star is. So that's one of the main thing we want to answer. And which are the codes which attain it? Okay, so that's what we want to answer. It's a slightly different formulation from what we had seen earlier. Similar formulations are also used in this topic called online learning, where this thing is called regret. This is the performance of your algorithm. This is the performance of some other algorithm which knows more. In this case, this algorithm knows more. It knows the actual distribution. And you look for the best algorithm in this class with this knowledge. So this is the best algorithm. So you compete with the best algorithm in a class for this parameter with more knowledge, and you want to minimize the difference of this. And that will be a reasonable benchmark to strive for, because it will say that even if you knew more, if you knew the exact distribution, you can't do much better than the algorithm that we are proposing, which is you have tied its hand behind its back because this doesn't know the distribution, but still it can compete with the algorithm which knows the distribution. So similar performance criterion is used in online learning, where this thing is called regret. Okay. Okay, that's the problem we are after. In order to answer this question about how large this Rn star is, we will introduce a slightly different problem, namely that of probability assignment. And we will see how this connects to the problem of characterizing this min-max redundancy Rn star. Okay. So this probability assignment problem, what we want to do is we want this distributions Qn. These are not necessarily IID distributions. So this is some distribution on xn, n-fold product of the original alphabet, such that, so we want to assign this Qn such that when you look at this divergence between Pn, the IID distribution from this Qn, okay, and look at the furthest guy from this Qn, max over Pn. Pn is a P is this distribution from the probability simplex on X. So P is in from this set here, and then minimize over all possible Qn. And just for concreteness, remember that this Q is in this. Maybe I'll make some space. This Qn is a probability over X to the power n. So this can be beyond IID distributions. We want to find out the Qn which minimizes this worst case distance. Okay, and this is something we'll call Rn star. We'll denote this by Rn star, capital R instead of small r here. So the goal here basically is to find this distribution, and this distribution will assign these probabilities Qnx for every sequence x here, and we want to find an assignment which minimizes this. If you recall something we saw earlier, this looks very much like the information radius that we saw in the dual expression for capacity. So information radius, we saw it in the interpretation of capacity as information radius. Okay, you can go back to that lecture on properties of measures of information. I think this must be in somewhere in unit the unit on the part on variational formulae. So we saw information radius there. Anyway, it's a self-contained definition. Find the minimizing Qn that maximizes that's closest to the worst case guy. So you can think of this Qn as the center of all these distributions Pn, and it's the closest guy from them. First question you can ask is that why can we do something better by going beyond independent distribution? Will the optimal Qn not be independent? So what you can check is that if you take Qn to be an independent distribution, then this will be q to the power n, and since divergence is additive, it will look like n times dpq, something which grows linearly in n. But in fact, we will see that there is a Qn which can make this very small. It can make it logarithmic in n. Okay, that's a very surprising thing, and it's outside the independent distribution. So there is a distribution which is outside all independent distributions, which is sort of closest to, which is sort of the center of all independent distributions. Okay, that's what we will see. But before we go there, the reason we brought in this problem is the following. So this is something we'll show now. Let me call this a lemma. We will show that Rn star is approximately Rn star. So this Rn star, the min-max probability assignment here, the closest guy, the information radius, is the same as min-max redundancy Rn star. More formally, we will show that this Rn star and Rn star, they differ by at most 1. I think it's greater than Rn star. Okay, so it differs by at most 1. So how do we prove this? So first what we will show is probability assignment gives a prefix free code. So how do we show this? Remember that from Kraft's inequality in the theorem, we saw that all we have to come up with a prefix-free code for the sequence xn is a sequence of length assignments which satisfy Kraft's inequality. So suppose you are given a probability assignment q. Let me make space. This is the lemma which we'll prove now. We make a little box around it so that we can see what we're trying to prove. This is what we'll try to prove now. Highlight. Okay, let's try to prove this guy. Given a probability Qn on xn, let Lx, the length of the sequence, the length that you associate with the sequence xn, we'll define it as two to the power, so we'll define it as log of 1 by Qnx. Okay, we will just use this prefix-free code for Qnx. If you do that, if you use this guy, first thing you can check is, it's easy to check, we've done this before, Lx satisfies Kraft's inequality. In fact, it satisfies this Kraft's inequality with equality. Okay, so that's something we can check, and I urge you to check it. And therefore, you can find a prefix-free code with these lengths. Therefore, for the prefix-free code associated with Lx, and we assign this length Lx to all sequences x from xn. We have, so for this prefix code, what's the average length? Expected value of L of x. Let's look at the average length of this prefix-free code under P when the symbols are drawn IID from P. So that's equal to summation over x, Pnx, L of x, which can be written as summation over x, Pn of x, log of 1 by Qn of x. Okay, but what I will do is I'll multiply and divide this guy by Pn of x. And then what happens with this same thing is, if you look at this guy, the first term here, that's minus entropy of h of p, so that's hpn. And the term that remains here is the divergence between Pn and Qn. Yeah. So this is entropy plus this, you can show. And what you have therefore shown is that this average length from the scheme under P minus the best that you can get under P is less than equal to dPn Qn. Okay, there is a small problem here. These lengths need not be integers, so we will just take a seal here. That's what the extra one will come in. And so then here, instead of equality, you will get this is less than equal to this plus 1, right? And so you'll get plus 1. So plus 1. Okay, and this is true for all P. This is true for all P. And therefore, if you minimize over all P, or if you maximize over all P, that's the worst case thing you will get here. So this you can maximize here over all P. And You maximize over all p and you look for the best distribution here. Okay, that's the one you will choose. But that best distribution here still will be worse than the best code here. So this implies Rn star is less than equal to Rn star plus 1. That's one side of the scheme. Okay. So one side of the bound. This is one side of the bound. We have shown this. So this we are done with saying that the probability assignment part, if you have a probability assignment, then you get a prefix free code. We saw how that happens. So this is exactly like Shannon codes, except that we're using the wrong distribution, and that gives you an extra cost of this way. Okay, how about the other side? So the other side, we say that prefix free code give a probability assignment. Okay. Okay, so how do we show this? How do we find a probability assignment given a prefix free code? So once again, prefix free code can be expressed by just lengths which satisfy Kraft's inequality. So given a prefix free code with code word length lx consider, so now I have to find a distribution associated with these lengths. So I'll define Qn of x as 2 to the power minus Lx divided by summation over all the sequences 2 to the power minus Lx. Okay, that's some distribution that I've defined. It's a valid distribution because when you sum over x, it sums to 1. So if you look at this distribution and you look at for this distribution, if you look at the divergence between an IID measure P and this distribution, that divergence is equal to summation over x P and x log of 1 by Q and x minus n times entropy of P, just by expression for divergence. But this guy here is equal to summation over x P and x log of so if you look at this this numerator here, it comes here and it becomes 2 to the power Lx plus this constant term plus log of summation over x prime 2 to the power minus Lx prime and minus NHP. So log of 2 to the power Lx is just Lx. So this becomes summation over x P and x Lx. That's just the expected length under P. So you take NIID samples from P and take expected length under that. Minus NHP. But you are still left with this extra term here. But that's where we'll use Kraft's inequality to claim that this thing is less than equal to 0, since this summation here is less than equal to 1 by Kraft's inequality. Okay, that's where we have used the prefix free nature of this code. So this is less than equal to this. And this is true for every distribution P on X. Therefore, if you take the worst distribution, the worst in the sense that maximizes this guy, that's still less than equal to the max over the worst distribution on the right side. Okay, and this is true. There is a Q like this, and therefore, if you put min over Q, it only can become smaller. But the important point is now this left side doesn't depend on this L, so it holds true for every prefix free code, and therefore if you take minimum of all prefix free code here, then still the inequality holds. So Rn star is less than equal to Rn star. That's the other side of it. So we have shown that capital Rn star plus 1 is exceeds small rn star, and small rn star is at least capital Rn star. So these two quantities are off by at most 1 bit. So for our purpose, we will just ignore this 1 bit and treat these two problems the same. So what we have shown is that this problem of finding min-max redundancy is the same as the problem of finding this Q, this probability assignment problem, where the goal is to find this Qn that minimizes the maximum distance. Just to recall this information radius interpretation, all these distributions Pn are some points in the probability simplex over P1 and P2, and these are different points, blah blah blah. This is probability simplex over Xn, and these are the independent distributions. We take a Qn point here and take its distance from all of them. This is the divergence that we are looking at, and we look for the Qn which minimizes the maximum distance. This maximum distance is the minimizing point for the maximum distance. So that's sort of like the center point here in this geometry of divergence, and therefore this quantity is called the information radius. So this information radius for ideal distribution is equal to the min-max redundancy Rn star. So we can either think of probability assignment or think of design of min-max optimal prefix free codes. Okay, I'll just note down this principle here. So universal prefix free code design is similar to the problem of, it's almost the same as the problem of min-max probability assignment. Okay, so you need to find out what probability model to use, how to assign probabilities to sequences, and these two problems are very close to each other. Okay, so in the next class, in the next lecture, what we will see is how to come up with schemes that are universal. We'll present the first scheme, which is a rather simple one, uses something called types, just empirical frequencies, to compress a sequence of symbols. See you in the next lecture.